Hi, everybody. Dr. Richard Smith here. I'm starting a special series of talks with fellow Foundation board member Ray Tomes. These conversations are a little different than many of the conversations we host here at the Foundation for the Study of Cycles. Ray has been working on cycles research for over half a century now. I believe it's closer to 60 years. And Ray is truly a mathematician and a scientist who has been studying cycles literally since he was a teenager. And Ray discovered the work of Dewey after he had already started his own research and started to discover his own patterns in cycles. And I think Ray, more than anyone else that I've met living today, is truly pursuing a science of cycles. I want to share briefly with you a quote that Ray brought to my attention from our foundation founder, Edward Dewey. Let me just pull that up here. Insofar as cycles are meaningful, all science that has been developed in the absence of cycle knowledge is inadequate and partial. Thus, if cyclic forces are real, any theory of economics or sociology or history or medicine or climatology that ignores non-chance rhythms is manifestly incomplete, as medicine was before the discovery of germs. So this is a quote from Dewey that he wrote in 1967. That was already more than 25 years after he started the Foundation for the Study of Cycles. And this is clearly what Dewey aspired to. So we cover a lot of different content, a lot of different cycles at the Foundation. Most of the time, though, we're talking about a cycle here and a cycle there in different circumstances. Maybe it's the markets, different types of markets. Maybe it's society. Maybe it's Ray Dalio talking about an 80-year cycle or the fourth turning of Neil Howe, et cetera. So yes, we talk about cycles a lot. What Ray is working on, though, is what Dewey truly aspired to, which is a science of cycles. What are the common cycles that we see throughout the sciences, throughout markets, throughout sociology, throughout climatology? And Ray has gathered those cycles and he has formulated a theory about how these cycles come to be, what gives rise to these cycles, what is the structure of cycles in our universe and in our lives. So that is very important work. It takes some time to work through Ray's theories and his very large body of work. And that's what this series of talks is about. So we're going to be slowing things down. We're going to be working through charts. We're going to be working through numbers. I'm working through the material myself to better understand it and to make sure that our foundation audience and more people around the world can understand Ray's work, and so that we can together continue to move towards a science of cycles that we hope can ultimately make the world a better place. So enjoy, take your time, go back and watch parts over again if they're not clear. Send in your questions for me to ask Ray next time. And I look forward to delving into this material with Ray and with you. Thanks so much. Thanks for your support. We really appreciate it. Enjoy. Hello, everybody, and welcome. I am Dr. Richard Smith, the chairman and CEO of the Foundation, and I am delighted today to be here with fellow board member, and particularly our science director, Ray Tomes. Hello, Ray, and welcome.
Hi, Richard. Thanks very much. I've been looking forward to this.
I'm really looking forward to it, too. I think your work is so important. I'm grateful for your involvement with the Foundation. I know that you were not happy with how the Foundation was going 10 years or so ago, and you actually started the Cycles Research Institute to carry on authentic cycles research. And I definitely think that you've been doing authentic cycles research is some of the most authentic that I've ever seen. So we are delighted to have you joining forces with the Foundation for the Study of Cycles now.
Yeah, it's been good. It's been good.
So tell us a little bit about your background. What's that?
Yeah, Yeah, a lot of good people in the foundation now. Yeah.
Yes, I think it's
Yeah.
going well. I look forward to continuing to branch out into other areas besides just finance.
Yeah.
Although, obviously finance is a key area for the foundation. And
It's how.
it's a data-rich space where you
Yes.
can detect a lot of cycles, right?
Yeah.
And but ultimately, I think that we need a scientific theory of where cycles come from, right?
Yeah.
And I know that's what Dewey was after, a science of cycles.
Yeah.
And from what I've seen, you're the one who's done the most to put forward a coherent theory of cycles.
Yeah. Thank you, Richard.
And
Yeah.
and you call it harmonic theory.
Yeah.
You believe all cycles derive essentially from harmonics of waves
Yep.
in the universe, and that all the structure in the universe is ultimately a harmonic of one wave or another.
Yes. And I think Dewey, like you, I admire Dewey and what he did, and particularly as he did a lot of it without computers.
Oh, yeah, incredible. That is what charmed me so much, was when I saw Dewey's original work in the archives.
Yeah.
These beautiful handwritten, obviously labors of love, data tables and charts, so beautifully done. It was like calligraphy almost, and I
Yeah.
looked
Yeah.
at it and I said, wow, that should be in the Smithsonian someday.
Yeah. Yes.
so,
Yeah. Yeah.
so yes, absolutely.
Yeah.
Appreciate it. So
Well,
how did you get interested in cycles yourself, and what's your background, Ray?
well, at school, I was interested in maths and science mostly.
Mm-hmm.
And probably the first cycles thing that happened was that some friends of my parents gave me a subscription to Sky and Telescope magazine.
Okay.
And after I'd had that for a couple of years, in the back of it, it used to have the sunspot numbers from two different ones. There was an American one and a European one that would put out the daily sunspot numbers. And I thought, well, what are these good for? I knew there was an 11-year sunspot cycle, but I plotted these daily ones to see what happened. And after a couple of years, it was evident there was another cycle of about 4 months. I thought, okay, what's that? And I started looking at it. And eventually I came to the conclusion that 4 months was the synodic period of Venus and Jupiter. So Venus and Jupiter and the Sun made a straight line every 3 months. Sometimes both planets on one side, one on the opposite side.
Okay.
And the period matched. And what's more, the maximum number of sunspots occurred at the time that they all made a straight line. So I thought, well, if that's true, and they are the 3 planets that have the biggest tidal effect on the Sun. So I was developing a tidal theory of sunspots. So then I looked at the other planet that has a tidal effect strong is Mercury. Jupiter and Venus are 2 strongest, then Earth, then Mercury, and then Saturn, but the other's quite a bit behind. So I started doing other combinations of the planets, and I did the same method that Dewey did in the early days, writing out long rows of numbers and adding them all up at different periods. And sure enough, in each case, there was an increase in sunspots when a pair of planets made a straight line with the Sun. So then I thought, oh, I've discovered something. I'll go and at that stage, I would ride my bike into the Auckland University, the Auckland Library.
How old were you when you were doing this work?
Probably about 15, 16.
Okay.
Yeah. And so I rode my
Not
bike.
what most 15 and 16-year-olds are doing.
No, it was weird. And I'd look it up in the library, all the books on the Sun. I went through them all, and I found one that said, in the 1800s, this guy had a theory that planetary alignments and tidal forces caused the cause more sunspots. And he said, in my opinion, this will be disproved with time. And I said, you're wrong. And that's been proved with time. But it was only a little later on that I found that right during this period when I was doing this, NASA were also doing it, because they had this situation that they were going to send some men to the moon. And they, once you get outside the Van Allen radiation belts, if the sun does some nasty fireworks, those guys can seriously get cancer or worse. So they were trying to work out how they could predict these things. And they tried lots and lots of things. People did lots and lots of theories. And the only one they found that worked any good was planetary alignments. Now, before that, if someone found that, they would have just swept it under the carpet and carried on and pretended they didn't notice, because it sounds like astrology.
Right.
And nobody wants to do astrology. Of course, people that go in markets are quite happy to do astrology, because they're trying to get a result for themselves, not trying to impress somebody else that I should have a degree for this. So it's not astrology, it's physics. Tidal forces are physics. Yes. Now, there's about 4 different theories for how sunspots arrive. And as far as I can tell, 2 or 3 of them have actually got some validity. So there's a combination of factors. But anyway, that was my beginnings. And I went to university not long after that, and I studied maths, applied maths, stat maths, and physics. So you've got a good idea of what goes on in there. I didn't get to do computer science then, because they didn't have a computer science course. But I went and I decided computers would be a good thing. I went along to IBM and I said, have you got any jobs? And they said, no, but our customers often have jobs. If you do an aptitude test, we can put you onto a customer. And they did. And it was New Zealand Insurance Company. And it turned out to be a really good place for me to go, because after writing some COBOL programs, they worked out, actually, this guy's better in Fortran, and we'll put him in the investments department, because they need people that can do some maths. So I ended up in the investments department. And at the time, it was run by an Australian guy named Peter Davies, who was a very, very bright cookie. And I learned a lot of stuff from him. And we kept in touch even when he went back to Australia, with doing stuff related to this. So I could write programs then to do some of that analysis with those things without having to do it all laboriously by hand. So that was the 60s. Later on, in the 70s, I ended up running my own little company called Tone Statistical Research. And I had NZI as one of my customers. And one of the guys there in the investments wanted me to try and do forecasts of interest rates, exchange rates, and what's the other one you got to do? Inflation, for what's going to happen on those, because at that stage, the New Zealand economy wasn't an open one. It was fairly closed. You could only move money between countries with a very good reason. And wanting to make money by doing exchange rates was not considered a good reason. But NZI made money overseas, and they had the ability to bring it back to New Zealand. The timing was up to them. So if I could predict exchange rate for them, then, excuse me, they could time those things. So I started doing some analysis of a bunch of economic variables. And as well as economic variables, my guess was that demographics and other things would be important too. So I had things like terms of trade, I had population, age distribution of population, and other stuff, terms of, and the prices of various important commodities. So when I did that analysis, I used some programs that they used at NZI. There was one called factor analysis, and I put a lot of this stuff in, and I did the factor analysis. And hello, this looks like some cycles. There was one very long cycle. I had 44 years of data, had about one cycle, and there are other ones around 4 years or so, 3 years, and one about 7 years, and a bunch of these. I'm going to start looking for cycles.
Well, let's start. I know you've got charts on this, so why don't we share your screen and start to get into the charts. All right, so I'm going to be asking a lot of questions as we proceed, and so we'll take our time. I got from that. This was 1977 or so. You can see where the graph stops at 77. Okay, so this is some data that you were looking at on behalf of a
This was the factors
insurance
that came out of
company
the
in New
analysis.
Zealand.
That's right. And they gave,
you pulled these factors, used a factor analysis to essentially find patterns in the data.
Yeah. What I was trying to do, or what I did do, is I was trying to use the state of the economy at 1 year to predict forwards. And I haven't got those ones in this display, but I should have. I found you could predict forward 3 or 4 years quite well, but after that, it wasn't doing much.
And so if we look at that factor 1, for example, from that looks a lot, that's a cycle, right? Bottoming in 1936 or so, topping in 1951 and bottoming in 1970. 71. So that's what, like a 40-year cycle?
Yeah, it looked like about 40 something, but later on, I gave a talk on all of this at the Statistical Association, and an economist got up and he said, "Oh, that long one you got there, that's the Kondratiev cycle." I said, "Oh, thank you, that's good to know." And these other ones, that's the Schumpeter cycle, and that's the who's the other famous guys? He mentioned a number of these guys' cycles. He said they don't exist. The only one that's real is that one, in fact, the 3-4, which is the business cycle. And I said, "Oh, that's funny. I wonder why they give names to things that don't exist." And anyway,
he must have been one of those guys that was more interested in his reputation than results.
But some other people got up, and one of them said, "Oh, yes, they do. That factor there is exactly what we see in the social services. The demand for services varies on that one." And someone else said, "Yeah, that one's this." And they all got up and said, "Yes, those exist in the things that we do." So
this is basically economic data out of New Zealand.
That's correct.
Now, you were doing this analysis in the 70s, and this was historical data going back, 45 years.
Yeah. And the interesting thing is those factors 3 and 4, I later on came across a couple of graphs and something that looked remarkably like those, and they were world money supply and world GDP growth. And they were basically
factor 3 is what, about a 1.5 or 3-year cycle, 4-year cycle?
It's about 4 years, yeah.
Okay, and factor 4 is what?
It's the same, but their phase is different. So it's like a sine wave and a cosine wave. They got the same period, but they don't correlate.
Okay.
Yeah. So then I decided, I wrote my own cycles analysis program. It was a funny way of doing it, because I did simultaneously all of those things. I looked for how strong cycles were present in them, and I got this graph.
Across all of the variables, which was about, you mentioned like 22 different variables, economic.
That's right.
Variables,
and I used the rate of change of them as well as the variables themselves. So I actually had 44.
Okay.
And there's a strong cycle there at 4.45 years now.
So you found the 4.45 year cycle in most of the variables.
Yeah, a lot of them, yeah.
Okay. So these were the strongest cycles that you found.
Yeah, those are the 4 strongest ones. Yes.
Okay.
Yeah, and it can't. The 9-year one's very rough because there's a general upwards trend, so you got to try and work out where it hits. But it looked like it was double the other one. And later on, I realised that if I multiplied the 9-year one by 4, the next one by 5, next by 6, next one by 8, they all gave answers close to 35.6 years. Then let's skip to when I got, later, it was some time, this was the 70s.
So let me just stop you there for a second. So what you're saying is that all of these cycles were essentially factors of 35.6.
Yeah, fractions
so,
of it.
36 divided by 4 is 9, 36 divided by 5 is about a little over 7, right?
Yeah,
and
divided by 6 gives
divided by 6 is about 6. And divided by 8, it's about 4.5.
Slightly under that, yeah.
So that's the common, common factor.
Yeah.
Amongst all these numbers.
Yes.
And that turned out to be a number that was also of interest to Edward Dewey.
Yeah, so let's skip through to Dewey's table. Oh, here we are. So I've put up here that graph, and beside it, Dewey's common cycle periods. So Dewey started from 17.75 years. He doubled it to 35.5.
I'm going to just get out my little marker here so everybody can follow along. So this right here is a table from Dewey himself, right? So this
Yes.
is your work up here.
That's correct.
Okay.
And I didn't know about Dewey then.
And you didn't
And
know
Dewey
about
didn't,
Dewey.
and he didn't know about me because I hadn't done it yet.
Right. And so this is work that Dewey had done around in the 60s or early 70s.
Yeah, I think so. I think probably in the 60s. I think it's in the case for cycles. I think it's
where Dewey was
67.
really looking for, common cycles across different phenomena.
Yeah.
And he found, he ended up kind of focusing on about an 18-year cycle.
Yeah.
As being in the middle, essentially, of all the different cycles he found. And then he basically took multiples and fractions of that cycle. So if we
going
look
up to the left and down to the right, he did ratios of 2.
Right. So
and going up to the
17 and a half,
17.75
17.75 times 2 is 35.5, times 2 is 71, times 2 is 142.
Yeah.
Divided by 2 is 8.8. Divided by 2 again, 4.44, etc. So up and to the left is times 2, down and to the right is divided by 2, up and to the right is times 3, down and to the left is divided by 3. And essentially that 17.75 number multiplied or divided by 2 or 3 gave Dewey almost all the key cycles that he observed in natural phenomenon and in markets.
Yeah, it gave him a lot of them. There's a couple missing, and we'll come back to that about how they actually do appear. But
your cycles are in here too, right? So we've got 4.44.
Yep, that's there.
4.45. We got 5.9, which is right here.
The 7.15 is not there, but he did find a common cycle of that period. It just doesn't fit in this table.
Okay, and then we've got the 9, which is close to 8.88.
Yeah, I don't consider
and of course, the multiples of all these being
35.5 was my 35.6, which excited me a lot.
So you were doing this work independently, and then you went and found out about Dewey and discovered that he had already made similar discoveries as you were making yourself.
Now, he had used a lot more data from a lot more places and in a lot more different things than what I'd used, and come to this pattern. I had used a lot less variables than him, but come to the same pattern. And my one was based on data, a lot of it a bit later than his, and from a different country. He wasn't using New Zealand data, and yet the same pattern was there. And as I found later, you can analyze all sorts of things and get these same things out. You can analyze the cycles in the solar system, for example, and get those periods, a lot of those periods.
Okay. So now we've discovered these cycles, and Dewey had discovered similar cycles.
Yeah.
And now we can start to talk about how harmonics theory, what it is, and how it can explain or account for these, the structure behind these common cycles.
That's right. So one of the other things I did around this time, I got some wheat prices, weekly wheat prices, because this data that I was using here from New Zealand economy was only annual data. So I got the wheat prices, and they were weekly, and I analysed those, and they had quite a lot of cycles present in them. And after a little while, I realised, hey, those periods taken as frequencies actually correspond to a lot of the white notes on the piano and 2 black notes. Then it was only then I realized that 4, 5, 6, 8, the proportion of those ones to 36 years is a major chord in music. So then I started saying, it's music, it's all music, and that lower triangle of Dewey's from 17.75 down to 0.22 and across to 1.11, that is Pythagoras's lambda.
So basically what you're saying is that up here on the top here, this is a major chord.
Yep.
If this were C, this is E, this is G, and this is the next C.
That's right.
The double, right?
Yeah. Yeah.
And then
it's going downwards because those are periods. So C is the 9.
Okay.
The lower C is 9, and you're going down, and the 4.45 is the octave.
Okay, so it's C, E, G, and C.
Yeah.
Okay.
That's right. Yeah.
And then down here. You're saying this is the Pythagoras lambda.
Yeah. Now,
And
as far
what
as
is the
I can
Pythagoras lambda?
Well, that was what he worked out by ratios of 2 and 3, how to get all the different frequencies. Now, he knows that he didn't entirely solve it, but he got the ratios that made pleasing sounds in music. So ratios of 2 to 3. So if you put the 5.92 cycle versus the 8.88, that's 1.5 times a period, times 3 divided by 2. And that will give you a major fifth, C to G.
Okay.
And you can do the other ones like that. That whole line running up the left diagonal, that's all the C's going up octaves, right? So
this one here.
that fitted.
This one?
Yeah, no, the other diagonal.
The other diagonal. Okay.
Yeah. They're octaves because each one is double the previous.
Right.
Yeah.
Okay.
Yeah. Now, in fact, the father of the famous Galileo, he actually said that Pythagoras didn't have it quite right, because he said a major chord is actually 4, 5, 6, 8. But in Pythagoras's one, you don't get a 5 over 4, you get 81 over 64. And he said, no, it would be 80 over 64. And I can confirm that he was in fact right. Pythagoras had this thing when he tried to go around all the cycles and back again by repeatedly multiplying by 3 and dividing by 2. He ended up with a little bit of an error thing, which was called Pythagoras's comma. And it doesn't quite work. And that can be explained. If we get to Indian music, we'll see how some of that all fits together, because that's one of the things that comes up is Indian music. They've got some interesting stuff that relates to cycles and the earth and our brains and everything else.
Okay.
Yeah.
Great. Well, let us start to delve into harmonics theory a bit at this point.
Yeah. Oh, yeah.
And proceed slowly.
Yes. This is a graph that I made, which has got every cycle that I found that was in the cycles book listed. And it's done by hand. It's not particularly accurate, but you can see there's some places with a lot more cycles. So at 4 months and 8 months, there's a lot of cycles. Now, 4 months and 8 months, 4 months was that period where Jupiter and Venus and the Sun made a straight line on either side. 8 months when it's on the same side. 2 years is a common cycle. There's other ones.
So these were occurrences, kind of frequencies of cycles observed by Dewey in the work that he had done of identifying cycles in nature.
By other people that reported to the foundation. Yeah. So all of those.
And so you just said if it occurred, then just put a dot.
Yeah, that's right.
So the most observed cycle was between 3 and 4 years.
Yep. Which he gave us 40.68 months.
The famous stock market cycle.
Famous stock market cycle. That's why it's the most commonly reported one.
Right. It's the most.
You can see the other one there, just under 6 years, and you can see something. You can see one at about 8 years and around 9 years.
And you plotted this all by hand.
Yeah, by just under 18 years. Yeah. And you can see that something at 36 years, and again around 53, 54 years. Now, when I saw the 53 point something in Dewey's table, I thought, oh, that's that long cycle I've got. It's the convertive cycle. And I mentioned the economist telling me about that. So this is the table that I came to when I extended Dewey's table. Now, so you can see in here, 35.59 years. So it's somewhere between my value and Dewey's. I think Dewey's figures were more accurate than mine. Were less accurate because I didn't have as much data, but they turned out to be closer in the end, and 17.79 years there. So
these are the cycle lengths.
Yeah,
that
years.
Dewey documented as prominent cycles from some observation.
Here, I've taken Dewey cycles. I've taken in astronomy, I shouldn't go to these other things first. In astronomy, a bunch of cycles were reported. One was called 155-day cycle. That happens to be around 0.4237 of a year. You see down the bottom row there. And other ones that were a third of that, and half of that, and a sixth of that, and double that, and so on. And those ones all were linked by racism 2 and 3. And some of those astronomers noticed that. They said these seem to be harmonics. And we actually get the sun's rotation period in there, 25.8 days, which is the 0.071.
So why? I mean, there's a lot of structure on this page, Ray, that I don't understand, right?
It took me some time to get to this.
So, like, what are these cycles down here?
Most of those are astronomical cycles.
Okay.
In the sun and other things, except the two on the left. 3.389 years is 40.67 months.
Okay.
So you recognize that one.
Yep.
And if we multiply it by 7, we'll get 23.72 years, which Dewey didn't have in his table, but which is linked in by ratios of 2 to the other ones he did have in his table.
Right? So these are primarily astronomical cycles or sunspot cycles?
The bottom set, yeah.
Okay.
The 3.389 was the stock market one, and the 1.695 year one was one I found in wheat.
Okay. And then we get into these cycles here. What are these? What's this cluster?
Well, a lot of those are Dewey's common cycles, right?
Okay.
53 contraditive.
And why do you have them in columns like this?
Well, I didn't like this diagonals with the 2 and 3. I put the rows of 2 horizontally. So I put the ratios of 2 horizontally and the ratios of 3 vertically, because it makes it easier for me to get these other groups.
I see. So this is, everything in here is, as you go to the left, it's 2 times. Yeah. And as you go up, it's 3 times.
That's correct. Yeah.
So you took the cycles that Dewey had observed and you put them into this 2 and 3 structure.
Yep. And I've made what I think are the accurate figures now. I'll come back to how I got to that. Shoot right up to the top now.
Sure. Well, let's go.
86 million years.
All right. So now we're up here at the top.
Yeah. Now, the first I came across the geological cycles was there's a book called Megacycles, which is the proceedings of a geological conference. And I've got a copy of it here somewhere if you want to see it. They said there's about a 600 million year cycle in geology, a 300 million, a 150 million, a 74, and a 37 million. So you can see that's that top line there, except my figures have got a lot more decimal places in them. Now, I knew that those 600 was going to be a little bit big because the 37 and 74 were going to double up to about 592 or something. I had this cruder version of this table originally. The mass extinctions of species were found to have a cycle variously given as 26 or 27 million years. And there are other cycles in geological ages and that have 53.3 and 26.65 million years.
Right. So these are the geological cycles here, right?
Yep. And the next one is mass extinctions.
These are mass extinction.
Yeah, the 26.
cycles.
Yeah. Well, that one. Now, that next row, the 1.11 million year, is a cycle in the solar system. Energy gets exchanged between Jupiter and Neptune, and the outer planets' orbits get slightly different and vary over that time period. It also shows up, the 1.11, in magnetic reversals of the Earth. And I believe the cause of that is because of these astronomical changes. So these periods, most of these other ones are astronomical, but in the middle section, you'll see 4,600 and 2,300 year cycles and 9,200. They all occur in the climate. And that 9,200 in the climate.
And these are just years, not millions of years.
That's correct. Yeah.
So everything, up here
says at the top millions of years.
Millions of years, and everything down here is just single years.
Right. Yep.
Okay.
And the 4,600 and 2,300 also turn out to be planetary alignments. The outer planets make very good alignments after those periods. And a number of people have put forward that those planetary alignments are the cause of those climate cycles. And I think they are.
But the bottom line is this is a catalog of significant observed cycles in nature, in the sun, in geology, in climate, etc.
Yep. And all the way from, they're the range of ones which I believe are linked by simple whole number ratios. So not just 2s and 3s, but down here we had a ratio of 7 to get to those ones. And I can't help but think that Dewey knew there was a 1.11 and a 2.22 year cycle. He must have noticed that there's an 11.1 and a 22.2 year cycle on the sun as well, which is 10 times as much. I think he didn't know what to do with that, so he kept quiet about it. But they are 10 times as much, which is 2 times 5.
Got to make sure we're all following you here, Ray. So when you have this 7 down here.
Yeah.
What is this 7 telling us?
That's the ratio between that block at the below it and the block above it.
So 3.4 here, 3.389.
Yeah.
Times 7 gives us what?
23.72.
23.72. Okay.
Yeah.
So basically everything in here, if you multiply it by 7, gives you one of these?
Yeah.
Wow.
Now,
and everything in here, if you multiply it by 5, gives you one of these?
Yeah. Well, a lot of them do.
A lot of them
I haven't got all the same ones, but...
so 5 is a common factor between this set and this set.
Yeah,
wow.
That's right. Okay. Now, the astronomers had mentioned 155-day cycle, right?
155-day cycle.
Cycle in the sun. Now, I was actually, the same time they were doing it, I was finding that one when I was doing the planetary ones. That one didn't fit with the planetary motions, but I found it. And I found a value quite close to that 0.4237.
So this 0.4237 is 155-day cycle. Okay.
Yeah. And if we multiply that by 7, what do we get? 0.4237 times 7. We'll be surprised if we don't get one, 2.966. So we get one on that group, right? Now, that's one of Dewey's common cycles, 2.966. So I'm linking these together, that block and that block by a ratio of 5, which clearly shows in a lot of the things that we see. And a lot of those are astronomical ones. The 11 and the 22 are the sunspot cycles. The around 89 and 178 and 355, they are all being reported as climate cycles as well.
All right, so this is a catalog of cycles from kind of different categories of phenomena, and they have some kind of factor or geometric relationships.
Yeah. Now, I decided
to each cluster.
I decided that I went and gave a talk about Harmonics Theory in the 90s, 96 I think it was, in Russia. And at that conference was Professor Athanasiev, who was a geologist who had done a huge amount of work on cycles. And he's written a book called, the title translated as Nanocycles Method. And he does this by studying all the cycles that are found in geological strata, and they allow geological strata to be dated because these cycles are due to the nodal cycle of the moon changing. So the moon, because of tidal action, the moon is gradually getting further from the Earth. And you will have come across the 9.3 and the 18.6 year cycles that are mentioned, which don't show in this table because they're not constant cycles, but gradually changing over time. And there was Louis Thompson used to talk about those a lot, stuff on agriculture. So he used that, and those cycles change over time. So at the current time, the 9.3 year, which is half the 18.6, is commonly found in a lot of things. But if you go forward 3 cycles of that, you'll get 27.9 years, almost back to the same season. And he realized that because rainfall often occurs in seasons, 9.3 years later, you don't necessarily get everything happening, but 27.9, it gets close. But then again, you get out a bit further, and it turns out that on average, it happens every 31 years. And you get that by dividing 9.3 by 0.3, you get 31 years. And there have been reports of 31-year cycles in Africa and other places in climate-related things.
Okay.
So
but still, bottom line, what we're looking at here is a catalog of cycles.
Yeah, but what I'm trying to get to
clustered into different categories, and now we're going to
But when I
ultimately
talk,
explain the structure of this through
yeah,
harmonics theory.
yeah. Now, I didn't have these accurate figures then, but Professor Afanasiev, after my talk, came up and thrust this book in my hand, shook my hand, and he doesn't speak English and I don't speak Russian, but my talk was translated. And one of the guys there told me it was an extremely good translation that the young lady did. And so I looked at his book and I saw, oh, he's got a table showing peaks of cycles, a bit like my one of the common cycle of the cycles things. Oh, we haven't done that yet. But anyway, I saw his 586.24 million year one and I went, yes. And so when I put that in his figure and calculated all those out, down here I got 11.86 years, which is Jupiter's period around the sun. And in fact, it gave 11.8622 years because his figure was that accurate, which is accurate to 6 digits for Jupiter's period around the sun. And I had always regarded that as a clock. It's 1/3 of Dewey's 35.5 years, right, more or less. And so I regarded that as the clock of the solar system because Jupiter's the most massive planet. Everything else gets synchronized to it, not the other way around.
And again, your interest in the planets is primarily tidal forces.
No, that was only tidal forces is part of it, yeah.
Okay.
It's not harmonics theory, but I can talk about my theory for how the planets influence the sun. Tidal force is part of it, but there's another one as well.
Sure. Well, why don't we get into the harmonics theory first?
So
and I think we're going to have lots of conversations about this, Ray. So no rush. We got a lot to cover.